Welcome to the SEI Podcast Series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
My name is Suzanne Miller. I'm a principal researcher here at the SEI, and today I would like to welcome my colleague, Dr. Jason Larkin, who is a researcher in the Emerging Technology Center here at the SEI. Today, we're here to talk about quantum computing, specifically the quantum advantage work that we're doing here and why this is important to the SEI and the federal government. Welcome, Jason.
Thank you. It's good to be here.
Glad to have you. And we are, as we have been the last couple of times, we're here remotely. So I hope that you will have some patience for us as we work through this. But before we get started in the quantum computing itself, I'd like to ask Jason a little bit about how did you get into this? This is not the typical, I'm going to be a quantum computing guy when I grow up. How did you get into quantum computing?
So I talked about this a little bit like on the Cyber Minute or podcast that we did with our intern Matthias, because the same question kind of got brought up. And I went into a little bit, but basically, I got into quantum physics back when I was in school, which is kind of strange because I was a mechanical engineer. But basically, when I went to grad school, I took a bunch of physics courses, and quantum physics was one of them. In fact, I took several quantum physics courses, and then I got to use that stuff in my PhD work, my thesis work. But this was like using quantum physics to model materials and other things. And then I put that stuff down for a while, for a couple years, until I started working at SEI. And by the time I started working at SEI, now quantum computing was starting to become a thing. And so kind of like I've done quantum physics on and off for a long time, but then I had a dormant period, but then it kicked back in because of this interest and funding that's in quantum computing. So I get to use I think I said in the podcast, part of my code got reactivated. In my own brain.
It's in your genes. So quantum computing is a subject that is coming up in the literature and in the news. First, give our listeners sort of what is it? What is the foundational kind of concept of quantum computing? And why is it difficult?
Oh, yeah. So fundamentally, it's about using new devices as the fundamental unit of computation, and these things are called qubits instead of classical bits or C bits, as they're sometimes called. And there are operations and behaviors of these qubits which are clearly different than classical bits, and these different behaviors potentially allow you to do things that are not able to be done on classical computers, or sometimes called classically intractable. And that just basically means that some computational task that you'd like to accomplish that has some use, we would like to do them on quantum computers, and we'd like to do them a lot faster than on classical. And so I think there's a duality. Like it's difficult for a few reasons. One is because it's still quite new as compared to classical computing and classical algorithms. And, it's been like the better part of a century we've been working on that problem. Whereas for quantum computing, the idea for it was really sort of solidified in the late 70s, early 80s, and then algorithm development has only taken place over a few decades time frame. So I think there's great potential for the technology, and I think that's also what makes it hard. In some sense, it's two things. It's hard because it's new, and it's by and large unfamiliar to computer scientists,
right,
and people like that. And then second, I think it's hard because the potential power that's there is tremendous.
So one of the things that I, in my reading about this, the classical bits are deterministic. You're a 1 or you're a 0, and that 1 or 0 state is what determines what happens next. But the qubits are probabilistic in some ways, and so that seems to be one of the things that, at least in that's one of the things that makes my mind kind of jump around a little bit and go, how can that be? So you want to say a little bit about that?
So I think maybe one thing to remember is we can do probabilistic classical computing as well. There's lots of ways of throwing stochasticity into a classical computation, but you're right. There is sort of the sort of thing that seems most different is this probabilistic nature of quantum computing, and what's more specific is the particular probabilistic nature of it, in that it's even different than what you can achieve probabilistically with classical computers. So it's like a particular flavor of probability theory. That's really, in some sense, like Scott Aronson has a very nice quote on this, where he basically reduces quantum physics down to a particular kind of generalization of probability theory. And maybe that's the most weird thing, is that really down at the subatomic, atomic level, and sometimes larger levels, that reality behaves probabilistically. And I can say that, like, from physics, like this idea about the interpretation of quantum mechanics, which relies on us having to treat all this probabilistically, like even that is not agreed upon, or I should say that it's a major point of contention in physics.
Sure.
But if we assume that stuff's true, and quantum mechanics or quantum computers behave probabilistically, or at least when you do the entire computation, you execute something on a quantum computer and make measurements, that process is probabilistic. And so this means that when we're designing quantum algorithms, they have to rely on this probabilistic nature, or not rely on it, but they have to confront, take advantage of it, accommodate it. Yeah, exactly.
Okay. So let's lead that into what is the SEI doing? We have an initiative called Quantum Advantage. So would you explain that to our viewers and tell us why is that important that we have this initiative, and what is it's important to us as well as to the federal government?
Yeah, so I would say that I think the way that we pitch our initiative in totality is like the search for quantum advantage, which I would say is also the what's driving most companies and researchers in general. And what people think is an example of quantum advantage was the Google quantum supremacy demonstration that happened last fall. And the definition is there's some well-defined computational task that we can execute on a quantum computer and a classical computer. And the question is, for that computational task, does the quantum computer outperform the classical computer? And there's a few different ways you can measure outperform or performance, but this is really the bottom line. So, like, we're spending all this money on quantum computing and spending all this time researching and developing them. What are they really good for? And maybe one step further, what are they game changing for?
Right.
So that's definitely like our initiative, and our goal is to try and find to find this quantum advantage the soonest. So there are a lot of things that we can look out on a 10 to 20 year time frame and say, if we have a big enough quantum computer with high enough fidelity qubits and operations, then we know we can do these classically intractable problems. But the harder problem is, in the next 5 years or less, what is the answer to that question? So what applications will we find quantum advantage for?
So are there things you're looking forward to that you think might be promising from that viewpoint? Is there something promising in that 5 year time frame that you can talk about?
Yeah, so I would say that there's initiatives across the board looking to answer this question. Whether it's like there's an entire DARPA project dedicated to answering this question. Like every one of the companies that are designing the hardware and building it and funding and all that. I would say that there's two or three, maybe more, primary focuses in what they call this Nisk era, the noisy intermediate scale quantum computing era. Perhaps maybe the first one, and maybe the one that has the most computational complexity or algorithmic complexity evidence that we would see quantum advantage. This is in material science. So this is looking at problems like trying to solve for the ground state of molecules or excited state of molecules, these types of systems. And I think that one could say that the computational complexity evidence is strongest for advantage in that domain.
Okay.
After that, people are looking at trying to do optimization. So what kinds of optimization? Optimization you might find in machine learning or in problems for like routing, scheduling, logistics. So these are like the traveling
Audio
salesman problem.
static management. Audio static management.
Yeah, sure. Um, so and then maybe another one which has a lot of focus is in machine learning, but like so there are some things I mentioned like in optimization that has applications of machine learning and other domains, but there is really a big focus on looking at quantum computing for machine learning. I think because probably because the business model or value proposition, if one found advantage in that space, is pretty obvious because of how much machine learning is pervasive now, and like every organization is looking at it. But I think maybe from what I can tell from the field, there is less, I wouldn't say hope, but there's less theoretical evidence specifically for machine learning that we'll see quantum advantage of the type that we would like to see it, like intractable advantage, like transformers.
So those are research areas that we still have to kind of work through and figure out, is this a viable area for us to put our research thinking on?
Yeah. I think those are three good like broad application areas. There are other applications. So this is all within like quantum computing, which I think is mostly the scope of what we're talking about. But we're also beginning to look at other aspects of quantum information science. So not just computing, but sensing, communications. Because you can imagine in like, they call this the quantum IoT, or this like this quantum Internet of Things. So now we can think about, well, in the future, if we're going to have quantum computers, and we're also going to have quantum sensors, and we're going to start connecting these things by a quantum network, now we really have a distributed like quantum Internet of Things. So we're looking at computing, and in particular those applications I mentioned before, but we're also trying to broaden because at the SEI this mission is in terms of technology readiness level. So we know quantum computers, if people keep going and they keep funding it, and we eventually get quantum computer with 1 million qubits with fault tolerance, and we know that there's classically hard problems we can do on that machine. We know there's going to be good things that will come from it. But like the best estimates right now is that's going to be 10 or 20 years away. So now the question is, like, within this domain, what's going to be available in 5 years or less? So I think we've begun to broaden our scope beyond just computing and looking at these other aspects of quantum information science as well, because I think that seems like what the SEI should be doing, given the mission statement and everything.
Well, and just from what you've said, I can think about some notional things that are in, say, what we call the last mile, where we have tactically disadvantaged computing. And if we have networks that are more probabilistic, that have this ability to really find the optimal path through something much more quickly than a deterministic kind of classical computing, then that could be something that's an example I can think of that would be attractive to emergency responders and others that are kind of in that last mile and technologically disadvantaged.
Yeah. So, or you can think of a situation where, like, we're going to have, instead of just having one really big quantum computer, it may be that, like we already have with classical computers, we have lots of smaller or intermediate scale computers, but we want them to share the information that they've processed. We don't want to just have a bunch of processors where we make measurement and collapse the state and so forth. We would like them to share their distributed computing in much the same way we do now with classical. That would open the door for, now we need a way of communicating the quantum information which is on these processors without destroying their state. And so, and then there's also the advantage that comes up with being able to send information which is encrypted or is protected rather by the nature that the information is contained in a quantum state. So we can I think moving forward for the SEI, I think it's important to like open up the portfolio, so to speak, because this allows one to select from it and figure out, what's the stuff that's going to transition sooner.
Right.
For example, quantum sensing, like quantum sensors are already available now, and they're being utilized in the field. And again, the same idea moving forward. So now if we have this world with lots of quantum sensors, perhaps we would like to have these quantum sensors communicate the output of their sensing to each other before the state is reduced to a classical state.
Gotcha.
So again, that this notion that going forward, maybe in the decades to come, we'll really be thinking about the quantum Internet of Things and about moving data around in a quantum way and all of that. So quantum information processing so the question I think with all this becomes like, given the TRL definition, what's the best candidate of all this technology? What's the stuff that's going to transition the soonest and all that?
So there's an aspect of that is sort of moving from one way to think about technology readiness levels is we move from pure research into engineering. And in your judgment, kind of where are we? Are we moving in? It sounds like in sensing, we're moving into the engineering realm already, but there may be some other areas where we're still very much in the research. What can it do? Kind of is that a good characterization of kind of the mixed bag of where quantum is at right now?
Yeah, I would say that, like for computing, for example, that we just recently submitted some work on looking at a quantum algorithm for doing optimization, and I think that, like, given what you just said, like, where is the status of this thing at? Like, what is the nature of the work? Like, is it looking at technology or an algorithm that you can execute next year and it's going to provide advantage in some mission context? Or is it really like looking at something that's further down the road? And I think that you can characterize the paper like the results in it are of a general nature, which I think in terms of, like, let's say a protocol, it's broadly useful for a lot of different optimization problems. And just, I think it generally looks at increasing performance.
Okay.
But the results of the paper make some assumptions, or you have to make some assumptions for the paper to interpret the performance results. And
Right.
these assumptions are basically that for the paper to be true, we would need quantum computers available that have much higher fidelity than we have available now. So then you can ask the question: so when would a quantum device exist that could demonstrate the proof of concept essentially that we have in the paper? And I think this is really difficult to predict because of how quickly progress is happening. So there are a couple different dimensions in quantum computing along which we seem to have a kind of Moore's law type behavior, an exponential improvement in performance. Not across the board, but there's a couple of different measures. But if you take this extrapolation and project it out, then it's more like what we demonstrated in the paper. If it's going to provide advantage, it's probably not going to do so until like 5 years from now, let's say.
Gotcha.
And with a big error bar on that projection, because it's like 5 years plus or minus 5 years.
Yeah.
not quite that bad, but
Well, and this is, the world we're living in today. We're seeing breakthroughs, that were not anticipated, certainly in many areas of technology, and this could be the next one. So for those that want to create the breakthroughs, what
Yes.
are, if you have an interest, if a viewer has an interest in quantum computing but really isn't that involved in it yet, what kinds of things would they be able to access from the SEI or other sources that you want to mention that would help them to understand whether this is a fruitful area for them to sort of put their own research thinking, or even if they're thinking about transition, say the quantum sensing is a little bit farther ahead, how would they get information about how to make use of that?
Oh, okay. So with respect to quantum computing, and I would say with quantum computing, it's making an impact there is, I think, a combination of things. So let me say first and foremost, like, we would like hardware to be a lot better. I mean, and maybe that seems obvious, but I think a lot of this depends on hardware getting a lot better, and I think a lot of let's say breakthroughs or algorithmic development, it really is going to require access to this better hardware, because sort of the whole point about quantum computers is their ability to do things which are classically intractable. Now we're still figuring out what exactly those things are and how much practical use they have, right? But that's sort of the point. And so that means that, like, there's a huge premium now and also moving forward with having access to these real bare metal devices. Bare metal meaning like the actual physical thing.
Right.
Because you just can't, there's no way to substitute for it. I mean, you can play games in classical computers and simulations, but you can only do that up to some point. So getting access to those is going to be very critical, I think, for like all parties involved, anyone who wants to make a dent, so to speak. Um, Beyond that, I would say that right now there's actually like kind of an explosion of content of like of ways of different approaches to understand quantum computing, depending on like what level you're coming in at, whether you're coming in like just as a computer scientist or a software engineer or something, you have no prior knowledge of quantum physics, versus maybe somebody who has quantum physics as a background, and across the board, right? But I think what we're seeing, and also participating in this process, are ourselves at SEI, one of my colleagues who helped to teach a CMU course last semester, and we can provide all this references and stuff in the transcript.
In the transcript, absolutely.
But yeah, we can provide a lot of different resources, and I think resources that span the spectrum of prior knowledge, because that's a real difficulty with this field. Is that depending on your background, you come in with different expectations, with a different agenda. Like, why am I looking at this technology? What do I care about it? Should I care about it now? Should I care about it 2 years or 5 years from now, right? And so I think we can provide a list of different references, which I think are useful for this spectrum of person who's coming in.
Gotcha.
So I think that's very important, because like how are you to decide, or how are you to determine rather, I think the fundamental questions we were asking, like how much should you care about this technology and when should you care about it? And it can be very difficult to determine that coming in, especially given the variation in background, and also given, I think, yeah.
Okay. So if you were to advise a computer scientist who's sort of just getting into that, we've got some resources. Are there particular areas where you would say, you know what, if you're new to this, this is the place to start? Sensors is the place to start. Where's a place to start that gives people an idea of what this is like to work in, but isn't necessarily the really deep research, kinds of focus?
Yep. So let's say in the references, I think we can do it like this. We'll figure out a set of references that's like, let's say 5 to 10 minutes in length, but really is worth, the bang for the buck. I can think of a number of different references. Like entry level would be 5 to 10 minutes. Like, tell me why I should bother with quantum computing, or why should I bother with quantum information science, or why should I bother with quantum sensing? Like, what's the fundamental thing which makes it attractive as a technology? Quantum communications, quantum key distribution, and so forth. So that's a good, like, 5 or 10 minutes, and like, what's the entry level? What's the entry level value proposition? Let's say. And then there's another tier, I would say, which starts to bridge into like the hour long. And for quantum computing, we can put a link to what I think is like the best use of an hour or an hour and a half for, like, let's say a data scientist or a software engineer. If you watch this for an hour or an hour and a half, this is going to give you like a tremendous, bang for your buck in terms of understanding, let's say for quantum computing, like what's the fundamental program that a quantum computer runs, and what are the fundamental operations of a quantum computer. So we have a good reference for that lasts about an hour. So we can go from like 10 minutes to an hour, and then
you can decide if you want to get deep.
Exactly. Yeah, and I think this stuff is very important, right? And one thing that's been really it's been really great to see with quantum computing is just how much content is being pushed out for a few different reasons. Like, a few of these institutions which are creating the technology, they also have a vested interest in training as fast as possible as many people about the technology. So there's a lot of open source efforts, and there's a lot of content out there.
That I think it's very I'm going to look at some of those resources, because I'm fascinated by this area, and because this is the most, I've been in this business for 40 years, and this is the most different, aspect of computing since I've been involved, since the early 80s. And so this is very cool stuff. Much stuff to learn.
It is cool, and I think that like the resources and all that stuff are great, because I think if you could like rank order for the technology, what are the most important things for it, and like a lot of people, number one, would say the hardware, at least for computing, and you'd be hard to argue against it. But number two after that has got to be like algorithm design and like the fundamental understanding of the technology and like people who have the understanding.
Yeah.
So it's like 1, 2, and then,
So if you're bored with your classical computing tasks, we have something new for you, right?
Yeah.
Yeah.
And by the way, learning quantum computing, it actually helps to bear fruit going back into classical land. So like right now, if you had to sum up like if the field stopped, like everything just ceased, all progress ceased, at least specifically with quantum money. The major advancement so far has been in a deeper understanding of computer science, of computational complexity, and of like improvement in classical algorithms.
Yes.
Like that's been the major benefits thus far, and it's not a trivial benefit. That's like there's been a ridiculous amount of new understanding just by considering what a quantum computer is and what are the computational complexity classes of a quantum computer and what implications does that have for the rest of the complexity classes and all that. So this would be the stance of like Scott Aronson and other like theoretical computer scientists working in quantum computing. Like they don't really care if there's ever a use case commercially for the technology. They're just happy that someone built one, and and perhaps Google violated the extended church Turing thesis, which they built a device that was that no one's built before.
And so this is, and I think that's important to say, that sometimes research like this doesn't necessarily take you where you think you're going to go, but it helps you to understand another area more deeply. So I know there's a resource called Q-Hub related to quantum. Right. Could you tell our viewers a little bit about how that works and how they would want to look at it in terms of its as a resource for quantum computing?
Yeah, so we made this Q-Hub, and it's basically just a Jupyter Hub server that we run, and we keep it up to date with all the different content that we as a group, and by that I also mean like as an extended group. So like people who use the resource are like myself and Daniel Justice and Catherine and other people in SEI, and we use it to do the work that we do, research and try to publish and all that. And then we also have an extended kind of group and network which connects to campus. So we have a few campus faculty and some of their students, and so it's basically a place where we can bring these people together, and we can configure the system with the necessary like software development kits, and potentially connect them to backends to like real quantum processors that are available from like IBM and Rigetti and D-Wave and all this. And then we use that to do the research that we do. So it's not some of the references and stuff I mentioned before about like 5 to 10 minute and then like an hour long. We use that resource primarily for people who have gotten through that level of content and are ready to try and actually publish something or do some research at that level.
An experiment.
Yeah.
Okay. Well, I want to thank you very much for joining us today remotely. And in addition to published works from your team, which we are going to link to, there's also a blog post that's recent on quantum computing. So we'll ask our viewers to go to insights.sei.cmu.edu and search under Larkin, Larkin, in the author's name field. That's the easiest way to find your blog post. I want to thank you, Jason, for being here and sharing your experiences and helping people to get an idea of why this might be important to them. To our listeners, I want to thank you for joining us today. We're going to include links in our transcript to all resources that we mentioned and some that we haven't really specified. There'll be some lists for you there. And as always, you can get these podcasts anywhere that you get your other podcasts, SoundCloud and other places as well. So I want to thank you all for joining us today and have a good afternoon. Thanks. Bye.
Thank you.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, Stitcher, TuneIn Radio, Google Podcasts, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.